Hello, bonjour, bienvenue, welcome. So another video for my science colleagues. One of my personal favorite uses of Excel is fitting data to a model equation. So to do this, you have to ensure first that you have installed an add-in called Solver. So if you search for the tools and the add-ins, you have to make sure that Solver is selected. And you only have to do this once for Solver to be now installed on your copy of Excel. You can find it under the Data menu. Now, to illustrate data fitting as efficiently as possible for this video, I've already prepared part of this spreadsheet in advance. So at the top, I've written out simple text describing the model equation that I'm going to use to fit my data. This is not a function, it's just annotation. So in this simple case, it's just a simple linear equation of y equals mx plus b. And I've presented x data and slightly noisy y data in columns A and B, and I've prepared a graph of these data on the right. Now there are 4 steps you need to follow to set up your spreadsheet for fitting using this Solver module. The first is to prepare cells that contain the values of the parameters that you're going to use in your model equation. So for this equation, those parameters are m and b, the slope and intercept. And I've entered values in cells D3 and D4 as initial estimates, but the values in these cells will be replaced by Excel as it goes through the fitting process. Now the second step is to prepare a column of cells that calculates the predicted Y value for each X value using the parameter values shown in the cells we just prepared. So this is where you have to carefully type the formula that corresponds to the model that you wrote out above in the annotation. So in this case, I would type equals D3 absolute reference for the slope times A9 for the X value plus D4 absolute reference for the intercept. Return. And I can double click the lower right hand corner of cell C9 to copy it all the way down the data set. And now you can see that I prepared this graph in advance to plot these data also. So the Y values predicted in column C, according to our estimates of m equals 1 and b equals 10, are not that close to the observed values. And we can improve them by manually entering different numbers, but that's the task that Solver will do for us. Now the third step is to calculate the difference between the predicted Y value and the observed Y value for every X value in the data set. So in statistical terms, this difference is called the residual. So this is an easy formula. I go to cell D9 and type equals C9 minus B9, return. And I can copy this down the length of the data table by double-clicking in the lower right-hand corner of D9. And now you can see that I prepared a second graph that plots this residual value against every X value, and I've arranged these 2 graphs so that the X axes are aligned. So this allows us to see how far off every data point is from the predicted value, from the best fit value, and it's obvious from this plot that our initial estimates are off because we see systematic variation in the residuals plot, and this should be improved upon fitting. Now, the fourth and final step to set up the spreadsheet is to calculate the sum of the square of each one of these differences, each one of these residuals. And this is called the residual sum of squares in statistics. Now, Excel has a powerful function to simplify this calculation. I can just go to cell D6, and I'm going to type equals sum SQ, open bracket, so sum of squares, open bracket, and now I'm going to select the entire array. D9, Control Shift, down arrow, close bracket, return. So now we're prepared to use Solver. So if it's been installed properly, we can find it by clicking on Data and then clicking on Solver. Now this opens up a splash box in which we have to enter parameters to specify how we're going to use Solver for iterative fitting. So for our application, we want to use Solver to consider the value in cell D6. That's the sum of squares of the residuals. And we want to minimize that value, minimize the sum of squares of residuals, by changing the values in cells D3 and D4. Now, we're not going to add any constraints to those parameters in this case, and theoretically for this model, we don't even have to make them non-negative. And the GRG nonlinear method for fitting, which was published in the 70s, it is excellent for virtually all regression applications. So we click on Solve, and nearly spontaneously, Solver has converged to a solution that minimizes the sum of squares of difference, and so we can click OK. Now you can see that Excel has replaced the values, the initial values, with the fitted values that provide the smallest sum of squares of residuals. And this gives a red line that fits really nicely through the data set. And the residual plot shows that the residual differences now are very small in terms of absolute value, and they're also randomly distributed above and below 0. And so the lack of systematic variation gives us confidence that the model that we've used is appropriate for this data set. But I hear you saying this was a lot of work to fit a linear data set, and you are right. We could have done the same thing in seconds by just adding a trend line through the data. But the lesson here is that this approach is not restricted to linear models. We can use any model we want. So let's look quickly at another example to illustrate nonlinear least squares regression. Now I've prepared another sheet in the same way, but this time I want to fit a mono-exponential association model to give a rate constant for these concentration versus time data. So I'm going to type the model formula into C9 following my annotation. The time-dependent product concentration would be equal to the final product concentration, F4, times 1 minus exponent of minus the rate constant. Let's make that absolute, times the time for that data point. Close bracket, return. Then I copy down by double-clicking in the lower right-hand corner of cell C9. Then I type the residual difference formula into cell D9 and copy down. And now I enter the formula for the sum of squares of those residuals. And now we're prepared to use Solver. And once again, we set the objective cell as D6, the sum of squares of difference. We want to minimize that by changing the values in cells D3 and D4. Now, in this case, because there's no such thing as a negative concentration for D3, and there's no such thing as a negative rate constant for D4, we're going to make the unconstrained variables non-negative. And we can still use the GRG nonlinear solving method and click Solve. So like that, Solver has found a solution. It has converged. It has replaced our initial estimates with the final fitted values of 100 as a final concentration and 0.039 as a first order rate constant. Again, the best fit line passes nicely through the data points, and the residuals show random distribution around 0 rather than any systematic deviation. So in future videos, we'll look at more advanced statistical evaluations, but for this video, let's simply note that the lower the value in cell D6, the lower the sum of squares of difference, the better the data set conforms to the model. Or more precisely speaking, the better that model accounts for the variation of the observed values.